Hi there, Nick here, M0NTV, and welcome back to my shack and to another video. And really this is part 2 of the little mini series that we started last time on designing a simple transistor amplifier. And last time we looked at the DC biasing of the 2 stages of that simple audio amplifier that I built. The first stage, the common emitter, and then the second common collector or emitter follower stage. Today, we are looking exclusively at the AC signal. And we're going to have a go at a bit of simple small signal analysis. Now, this won't be everybody's cup of tea, and that's fine, right? In which case, I'll see you on the next video, which I promise will be far more practical and to the point of building this direct conversion receiver, which I could have built several times by now if I hadn't keep disappearing down these rabbit holes. But having said that, I think they are important rabbit holes, and today's video is a long video. I mean, it's long for you to watch, I'm sorry about that, but it was a heck of a lot longer for me to put it together because there's a lot of material here and some of it's pretty complex stuff. And I've done my absolute best to ensure that the material that I present here is as clear and as accurate as I can get it. But I'm not perfect and I'm certainly not an expert. So the purists will probably look and think, well, you ain't done that bit right. You know, I apologise in advance for that. One thing I can think of instantly is that, you know, when you're referring to AC qualities, you're supposed to use all lowercase letters. I've tried to do that, but I know I've probably missed a few. So apologies for that. Having said that, hopefully you will see what I'm saying here. And I just hope that actually this video and the last video, and if you haven't seen the last video, you might want to go and watch that one first because this one will make a lot more sense. But I hope it will give you some tools and some confidence to have a go at designing and analysing your own simple circuits. So with that, feel free with this video to stop it, rewind it, fast forward it, whatever you need to do to get the most out of this material. But I do hope that you find something useful here, and as always, I hope that you enjoy. Well, here we go. Let's do some small signal analysis on that simple transistor amplifier that I designed in the last video. And the first thing to say is you may notice that the values of those resistors are different to the design that I showed you in the last video. And that's because subsequent to making the last video, I've done some more load line analysis, and I won't go into that now, but it turns out that my values that I picked, which was a quiescent collector current of 10 milliamps, actually wasn't the best, really. It was a bit too high, and I found that if I reduced the collector current and increased the voltage between the collector and emitter, then I could get a bit more headroom for the signal to swing, and it turned out that actually 8.5 milliamps was much better. So what I did is I followed the procedure that I showed you in the last video and just started with an IC of 8.5 milliamps and recalculated and got these values. Now, we're going to be starting with these 3 given values here up in the top left. So we're going to use this lower value of collector current. I'm going to use a beta of 308. That is simply the value that LT Spice uses for its 2N3904 model, which is much more than the 173, I think, that I more or less guessed at in the last video, but less than the, I think it was about 350, which was the actual physical transistor I tested myself. So 308 is close enough. You've got to go for something. So that's what we're going to go for. 8.5 milliamps quiescent collector current, beta of 308, and that actually gives us a slightly higher RE, little re, or R sub E as it's sometimes called, this intrinsic resistance between the base and the emitter of 2.94 ohms rather than 2.5 when we had 10 milliamps. So that's the circuit that we're going to be looking at. And what we're going to be doing today is some small signal analysis. So what is small signal analysis? Well, this is examining the way that the circuit operates from the point of view of our AC signal only. Now, last time we didn't care about AC. We were sorting out the DC biasing, which we needed to. And for the purposes of today, we're going to assume that DC biasing is there, it's working, it's in place, because otherwise the transistor wouldn't work, of course, if we didn't have that DC biasing. But that's the beginning and end of it. Well, we don't care about the DC at all in this video. We're just only concerned with how this amplifier works for our AC signal. And this will enable us to calculate three important characteristics, and they are, first of all, the input impedance of the circuit, secondly, the output impedance, and then thirdly, the voltage gain. Now, I say impedance, the truth is, really what we will be calculating is a pure resistance. We're going to be ignoring reactance, and I'll come on to say a bit more about that in just a moment, and assuming that we have a pure resistance. So although I'm calling these input impedance and output impedance, in truth they are resistances. But before we do that, we need to do some other work before we can make those calculations. There are four basic steps that we need to take before we can calculate those three things we've just mentioned. And I'm gonna tell you what those four things are now, and then we're going to break it down. I'm going to take each one in turn and show you how it's done. So the four steps that we need to take are, first of all, we replace all capacitors with short circuits, just a wire basically. We replace all DC voltage sources with the same, with shorts. Thirdly, then we're going to redraw the circuit in the light of what we've just done there and simplify it as best we can. And then finally, we're going to replace the transistor with an appropriate small signal model that will help us to define its behaviour with respect to an AC signal. So those are the four steps, so let's crack on. So the first thing we're going to do is replace all the capacitors in our design with short circuits. Why? Well, it's a fair question to ask. Well, what we're going to assume is that all the capacitors that we've got here have values of capacitance high enough so that their reactance at our frequency of interest is so low as to basically be ignored. Let me just explain what I mean by that. You've probably seen these graphs before. So this is frequency on the x-axis, increasing frequency, and then reactance on the y-axis. Now, if you're not sure about what reactance and impedance are, then you perhaps just need to pause this video and go and watch the one that I did on what is impedance, because I go into all of this in much more detail there. So I'm going to assume that you know about that. And the truth is that reactance is a kind of like a frequency sensitive resistance in inverted commas. It's not a resistance, but it behaves like one depending on the frequency of the signal that it encounters. And actually, capacitive reactance decreases with frequency. So we're going to assume that the capacitive reactance is so low that we can basically ignore it, and those capacitors will just look like short circuits to our AC signal. And So that's the formula if you're interested for capacitive reactance. So we're just going to make an assumption that the value of our capacitors is high enough that actually the reactance is so low we can pretty much ignore it. What it does mean though is that if you're building this amplifier or any amplifier for different frequencies, we need to be aware of that. The resistors are fine that we've chosen, but the capacitors won't be. So let's say, for instance, if we were building this amplifier for 7 megahertz, let's say it was a little RF preamp, you wouldn't put 100 microfarad capacitors in there. You wouldn't need anything like as high as that. I would just stick in 100 nanofarads as coupling capacitors here and probably here as well. And 7 megahertz with 100 nanofarads would give us a reactance of 0.23 ohms. So hardly anything at all. So that's fine. However, if we were to stick with 100 nanofarad caps and then put this signal through it with, say, a 1 kilohertz frequency, we would have a reactance of 1.59 kiloohms. So that's clearly going to be no good at all, which is why I went for big capacitors, because 1 kilohertz at 100 microfarads is 1.59 ohms, so very little. So that's why we're going to replace the capacitors with shorts. We're going to assume that the reactance is so low that we don't need to worry about it. So let's do that. We take them out and we replace them with the wire. Okay, so that's got rid of the capacitors. We don't need to worry about that. Second step, we're going to replace all DC voltage sources with shorts. Now, this one takes a bit more thinking about, because, you know, you think, well, I get about replacing the capacitors, but why on earth would a DC voltage source look like a short? Well, it's because a DC voltage source provides a constant voltage irrespective of the size of the load that you connect to it. Now, I don't need to tell you this. If you've got a DC power supply on your bench or something, you know this. You know, if I'm running a circuit at 12 volts, I'll fire it up, I'll dial up 12 volts, and I expect that the load, my circuit, will see 12 volts. And I expect that whether it's a circuit with a very high impedance that draws very little current, but I'll also expect it if it's a circuit that draws more current, I want it to get 12 volts. And that's what a DC voltage source does. It provides a constant voltage, irrespective of the size of the load connected to it. But it also presents a fixed, unchanging voltage with respect to time, because it's DC. So it's going to be 12 volts, 5 seconds later, half an hour later, 2 days later. You know, that's the point. It's not going to change. Unlike AC, of course, which does change its voltage with respect to time. So, for an AC signal, a fixed voltage of any level just looks like a baseline. You know, the zero crossing line. Think of a sine wave. The sine wave goes through its positive excursion, it reaches its crest and it dives back down, it crosses the line, goes through its negative excursion, reaches its lower crest, and then it goes back up again. And actually, it doesn't really affect the character of the AC waveform at all. All you're doing is raising it up or lowering it down a bit, but the waveform is what it was before. And so actually, you know, if it makes no difference whether the bias level is at 12 volts or 6 volts or 0 volts, it might as well be at ground. And that is what we do. Because our DC voltage source looks like a short circuit, and because the negative terminal of it is connected to ground, it just looks like another short to ground. Let me just illustrate this. So here's our typical sine wave then. Let's say it's sat at 12 volts. Now, what I need to just say here as well is I'm not talking about the way the signal goes through the transistor. Now, clearly, as we spent the whole of the last video looking at, DC biasing is really important. And it does make a difference, because if you don't have it high enough or low enough, you'll get clipping. We're not talking about the transistor. We're talking about how the AC signal sees this, the DC voltage source. And all it sees, if you had a bias level of 12, it would sit on the 12 volt line. But if you reduce the bias to 6, it would sit on the 6 volt. There's no difference, right? Or if you grounded it at 0 volts, it would look the same. And so that's why we can do with the DC voltage source what we've just done with the capacitors. We can take it out and we can ground it. Now, this changes things, doesn't it? Because look here, on this voltage divider, we had R2 went from the base to ground. But now look, if this is now ground, it means R1 goes from the base to ground. So this is now in parallel with this. So that's why the next stage is to redraw the circuit in the light of the changes we've just made and to simplify it as much as we can. So that's the first thing we're going to do. We better sort out. So this resistor is in parallel to here. So let's put it down here so that it looks a bit easier to see. So we move that down there. Yeah, we connect that up to the base and we connect it to ground, and we can get rid of those wires because we don't need them. So that's the first thing we can do. Now, the second thing we're going to do is we're going to look at the emitter, because remember we had a capacitor here which we've shorted out, but that means we've shorted out this resistor because this is going straight to ground. So it's like this resistor doesn't even exist to the AC signal, right? It's completely invisible because all the current's going to go through here, not through here. So we can get rid of RE, big RE, okay? There we go. And finally, this collector resistor, which was connected to the DC voltage source, that now is connected to ground. So we can bring that round here as well, because that's going to go from the collector down to ground. So let's move that round as well and put that round here. So that makes a bit more sense. Tidy that up. Okay, what else can we do here? Well, these resistors, R1 and R2, this is the base voltage divider. We can actually combine these because these are in parallel with one another. And so that's the next thing we're going to do. RB is the resistance on the base, the resistance connected to the base. And RB is going to be R1 in parallel with R2. So that's what we're going to do. We're going to parallel these two and get the value. So to calculate that, when you've only got two resistances, it's simply the product of those resistances divided by the sum of them. So 33k times 6.8k divided by 33k plus 6.8k. You're going to be doing this sum quite a lot. And that gives us an overall resistance of 5.64 kiloohms. That is the parallel resistance connected to the base. So let's reflect that. So we take that off. We call this RB, and that's 5.6k. Now, this is as simple as we can get it now. We've got it down to an AC signal source with a transistor, one resistance between the base and ground, one resistance between the collector and ground. So we can't simplify it anymore, but what we can do now is we can have a look at replacing the transistor itself with an appropriate small signal model. Now, there are various models that you can use. I'm going to use one which is called the hybrid pi model. And this sees the transistor as though it were, well, in this case, a current-controlled current source. You can view it using the hybrid pi model as a voltage-controlled current source. You would do that for different reasons. I'm not going to go into that now. So we're going to see it as a current-controlled current source. Now, what you need to understand here, as you look at this diagram here, all of this is this, right? So ignore RB and RC. In a minute, we're going to drop this into here and replace this. But all we're looking at is the actual transistor itself. And what this is an attempt to do, in order to help us to calculate the input and output impedance and the voltage gain, we need a more detailed model to help us to calculate the values of the things that the transistor is actually doing and some of the stuff that's going on within the transistor itself. And that's what this model seeks to do. It's a model, no models are perfect, but this is what we're going to use. Now you will see here that there are two values here either side of this current source. So you've got a current source here, which is defined by beta 308, IB, the base current, beta times the base current between the collector and the emitter. Well, that makes sense. And then you've got a resistor here between base and emitter, and a resistor here between collector and emitter. And I'm going to talk a little bit now about what these two values are, R pi and R sub O. Well, R pi is the small signal input resistance between the base and the emitter looking into the base, right? So this is the resistance that an AC signal will see going from base to emitter looking in to the base. How do we calculate that? Well, the way we calculate it is it features this R sub E, or little re, whatever you want to call it. And so we're looking at what the signal will see. Looking into the base, well, it's going to see this intrinsic resistance between the base and the emitter. But because of the amplifying effect of the transistor, we're not just going to see R sub E, we're going to see the amplifying effect of that, beta plus 1. Now, why is it plus 1? Well, as we know, if we're taking the signal out at the collector, as we will be in this common emitter amplifier, we would have beta, the gain of the transistor, times the base current here. At the emitter, we see the same, plus 1. What's the plus 1? Well, the plus 1 is the actual original base current itself, which is flowing from the base to the emitter. So we're seeing R pi is beta plus 1 times little re. Now, if we hadn't bypassed our emitter resistor, it would be Re plus big Re, R sub E plus big Re, the emitter resistor. But as we bypassed it, we don't have to worry about that from an AC point of view. But just to let you know that if you weren't bypassing your resistor and the emitter, then you'd have to add that. So it would be beta plus 1 times R sub E plus capital Re. But we bypassed it, so we don't need to worry about that. So when you do that, our beta is 308 plus 1, it's 309, multiplied by R sub E, the intrinsic resistance between the base and emitter, and that gives us an R pi of 908.46 ohms. Okay, I'm going to take that away just to give myself a bit more room, because we need now to think about R sub O, this resistance here. So if R pi is the small signal input resistance between the base and the emitter looking into the base, R sub O is the small signal output resistance between the collector and the emitter looking into the collector. Okay, so this one is we're looking into the base at what's between the base and the emitter. This one we're looking into the collector between the collector and the emitter. And R sub O is VA divided by IC. Well, we know what IC is because that's the quiescent collector current, 8.5 milliamps. What on earth is VA, you're probably asking? Well, VA is the so-called early voltage, named after Jim Early of Bell Labs. And let me just show you this familiar graph. You don't need to worry about this too much, but just notice that on the x-axis here we have the voltage between the collector and the emitter. On the y-axis we've got increasing collector current, and then these green traces are different levels of base current, 50 microamps, 100 microamps, etc. Now, if our transistor was perfectly linear, then all these green lines would be perfectly flat. But if you notice, they're not. They curve up slightly. And that's due to something called the Early effect. And it's actually to do with the actual physical construction of the transistor and the junction and the depletion region in the transistor. I'm not going to get into all that now, but essentially what happens is as the collector to base junction gets increasingly reverse bias, as the collector to emitter voltage increases, so does beta, so does the gain a little bit, which means that the collector current increases, and so we actually get more collector current as the VCE increases. And the so-called early voltage is this curving effect is extrapolated back where the line crosses the horizontal axis and can vary between, well, 80 to 200 volts. Commonly, the early voltage is approximated to 100 volts, and that's what we're going to use. So when we calculate this, we get 100 volts divided by our quiescent collector current, which is 8.5 milliamps, which gives us an R sub O of 11.76 kiloohms, which is pretty high, which is good. And you remember when we talked about the ideal voltage source and how we were able to kind of short circuit that to ground from an AC perspective, because an ideal voltage source, of course, has zero internal impedance. Because if you think about it, even if your desktop power supply had a little bit of internal impedance, whatever you connect to it, you've got a voltage divider effect. So you won't be getting the full amount of voltage because some of it is dropped within the internal resistance of the device, right? So in order to make an ideal voltage source as ideal as possible, it needs to have as low an impedance, internal impedance, as possible. And so an ideal one has zero, so it looks like a short circuit when you take the voltage away. But an ideal current source is the kind of opposite. If you want your circuit to have a fixed amount of current, really you need internally to that current source for it to have a very, very high impedance. Because if it has a lower impedance and you connect your circuit to it, then there's going to be more current flowing internally in the current source than there is in the circuit that you want a fixed current flowing through. So it's kind of opposite problem. So that's why an ideal current source has an infinite impedance in parallel with it. Well, clearly 11.76 is not an infinite impedance, but it's a lot higher than the value that we're going to be hanging on it in parallel. And so actually what it will mean is this is so high that actually our collector resistor becomes absolutely key in determining particularly the output impedance. So it's a high value, this. Anyway, I've taken a bit of time on this because I wanted to explain what these values are. And I wanted to calculate these values here, because if we calculate them now at this stage, when we get to doing some of the calculations that we want to do, they will be simpler because we've done the hard yards now and defined and calculated R pi and R sub O. So what we need to do now is take our small signal transistor model and replace the transistor. So I'm going to take this away now. So just take one last look at this. We've got the transistor here, we've got RB here on the base, we've got RC here on the collector. We're going to put this into here now and redraw it like this. So all this bit in the center is the bit we've just been looking at, and we're going to add to it now the parallel resistance of R1 and R2, the voltage divider on the base. So that's going to come in parallel here on this side. And RC, the collector resistor, is going to be paralleled on this side. And it means now, and I've put the values down here as well that we've got. So we've got 5.64K, the parallel resistance, which is RB. I've put the R pi value in there, small signal input resistance between the base and the emitter looking into the base. We've got the value for R sub O, small signal output resistance between collector and emitter looking into the collector. And then I've got RC, the collector resistor, in parallel there as well. Now, we can do some calculating. So first of all, let's calculate the input impedance. And as I say, I'm saying impedance, but really it's resistance. So because we've spent a bit of time and already calculated R pi and R sub O, this will be a bit easier, because the input impedance is simply RB, the parallel combination of our voltage divider resistors, in parallel with R pi, which you'll remember is beta plus 1 times anything hanging on the emitter, which in our case is just little re, R sub E. So we do that. So we've got 5.64K, which is our RB, in parallel with 908.46, which is our value for R pi. And when you do the maths, yeah, here we go again. So yeah, let's multiply them and then divide that by the sum of them. And that gives us an overall input impedance of 782 ohms. Hallelujah. Let's put that one down. That's one down, 2 to go. Right, let's look now, secondly, the output impedance. And actually, again, drawing it like this, it's much more logical. The input impedance we've just seen is this resistance in parallel with this resistance. So it's perhaps not surprising. The output impedance is this resistance, R sub O, in parallel with this resistance, our collector resistor. So that means we've got 11.76K in parallel with 635. Remember what I said about this resistor being so large in comparison with this one. And as you'll know, when you parallel two resistances, one much larger than the other, the defining resistance will be the smaller one. And depending on how much larger they are apart from each other, the resistance value will be closer and closer to that smaller resistor. And you'll see this happen here. So Z out then is exactly the same. You multiply them, then you divide it by the sum of them. and that gives us an output impedance of 602 ohms. Fantastic. So let's put that down here as well. So with the input impedance, we've got the output impedance. Now, to calculate the voltage gain, I find it's easier not necessarily to look at the small signal model, but to go back to the original schematic, and hopefully you'll see why in a moment. So let's bring the schematic back again. Well, how do we calculate the voltage gain? Well, actually, the voltage gain is essentially minus, I'll say Y in a moment, RC, this resistor here, over little re, R sub E. Now, as I put here, plus RE if not bypass. So, if we weren't bypassing this resistor with this capacitor, if this capacitor wasn't there at all, in reality, not just, shorten it out or anything, if it just wasn't there, then actually you could pretty much approximate the voltage gain just by dividing this resistor by this resistor, because R sub E is so small, it didn't really make a lot of difference. But the proper way to do it is to say minus RC, this one, divided by whatever's on the emitter. So that's R sub E, the internal resistance, intrinsic resistance of the base emitter junction, on its own. If this wasn't bypassed, it would be plus RE as well, but as it is bypassed, we don't need to worry about it. It's just minus RC over little re. Why is it minus? Well, simply because we're measuring here at the collector. And as you will recall, hopefully, that the signal at the collector is 180 degrees out of phase with the signal at the base. So it's inverted, basically. And as you'll see when we look at the next stage, the common collector, we don't have that issue because the signal at the emitter is in phase with the base. But here it's inverted, which is all that minus tells us. So let's do it. So it's minus 635 here over 2.94 R sub E, which gives us a voltage gain of 216. Very impressive. And actually, let's put that down here. Yeah, 216. So, and just to calculate the dB, and remember it's voltage, so you need to do 20 log, 46.7 dB. So, a lot. What you can do, of course, is particularly if you want to stabilize this circuit, is sometimes people want a little bit of resistance here from an AC point of view. So you could split this resistor. So you could say, well, let's have a 100 ohms resistor in series with a 39 ohm resistor, say, and we'll bypass for AC the 100 bit, but we'll keep the 39 ohms in, so the AC signal will see that. So when you're doing this calculation, it would be minus RC over RE plus 39 if you did that. So anything that's not bypassed, you've got to fling into this equation, essentially. Or if you were designing it and you wanted a fixed amount of gain, so you don't have to settle for that. But by that way, you can tweak it however much gain you want to see. Right, let's have a quick look at calculating the capacitor values. Simple truth is, I didn't. I knew it was an audio circuit, and I knew I needed pretty big values, so I just stuck in two 100s and a 220 microfarad. But if you want to do it properly, this is how you do it. So the minimum value of C1 needs to be 1 over 2 pi F, which is the lowest frequency, in our case would be 300 hertz, times R. Well, what's R? R is the resistance, but actually the resistance from our point of view here is actually the input impedance or the input resistance. Because what's happening is this series capacitor is seeing the input impedance of our amplifier, as it were, a parallel resistor. So basically it's a simple RC filter. It's a high pass filter. That's what we're actually built. And so we need to plug those values in. So it's 2 pi, 300, the lowest frequency we want to use, 782, which is the input impedance. And if you do that, you get a value of 678 nanofarads. So you can see, talk about overkill. I'm way over that. The reason I am way over that is because, bear in mind, this is functioning like really a 2-component RC filter, because all the impedance looks like one resistor basically in parallel with this series capacitor. So we're not talking brick wall filters here, people. You know, it's a very gradual slope. So basically, the bigger you can get this, you know, the more you're going to drive down that reactance at the frequency that you want. So that's why I've gone a bit kind of overkill as well. But I thought it was important to show you how to actually calculate them. And you won't be surprised to know that the output coupling capacitor is very similar, except the R this time, surprise, surprise, is the output impedance. So when we plug that in, it's 1 over 2 pi 300 times 602, which is the output impedance. And that gives us 881 nanofarad. Yeah, I could have stuck a 1 microfarad in there, but as I said, I wanted to make sure to keep that reactance as low as possible. What about the coupling? Well, really, C3 needs, as a rule of thumb, to be very low in its reactance compared to RE, the resistor on the emitter. The reactance needs to be 1/10 of the resistance here. So if we want C3 to have a reactance which is 1/10 of RE, that is the equation: 10 divided by 2 pi times the lowest frequency, 300 hertz, times the value of RE, which is 140. And when you calculate that, you get a much higher level, 37.9 microfarads. And again, I went overkill and put in 220. Right, let's have a quick, brief sprint through the second stage. I'm not going to spend much time on this. You might have to pause this and watch it again. But a lot of what we're going to use now, we've already looked at. So hopefully you can apply the same principles and do the same thing. This is our second stage. It is an emitter follower, a common collector. So we have no resistor here on the collector. We only have a resistor here which controls the current and the biasing here on the emitter. And we've got our 12 ohm load, which is my loudspeaker, which is connected capacitively here. So I'm going to do exactly the same things. I'm going to short these out, these capacitors. I'm going to short out the DC supply. I'm going to simplify. You can see what's going to happen here. R1 is going to come down here and be parallel with R2 to form RB. Right, let's do it. Okay, so this is the whole thing. This is not just the model of the transistor. This is the whole thing. Just to save some time, I've put it in. What you need to be really careful of here is this is a slightly different model, because it's a slightly different model of amplifier. But note, the emitter is up here, the collector's here. This is because the collector is connected to here. But if this is grounded, that means that actually the collector's at ground. So the collector now is down here. On the last model that we looked at in the common emitter, it was the emitter was down here and the collector here. So it's like, if you imagine a 2N3904 transistor with a base pin in the middle, it's like flipping it over so it faces the other way. So the base pin's still in the middle, but the collector and the emitter are the other way around now, right? Okay, so you need to be careful with that. So the base is still here, but now this is the collector and this is the emitter. And so I've done what I said. I've paralleled these two resistors to form RB, which is 4.8K. We're going to need to use, for this, the input impedance of the signal coming in, and we know what that is because it's the output impedance of the last stage signal that we calculated, which is 602. We call this R sub S. This is the resistance of the source signal. We've got little re in here, and because this is operating at 10 milliamps, we're back to a little re or R sub E of 2.5 ohms. We've got R sub O here between collector and emitter again, and this is 10k for this device here. I did the same calculations, and we've got RE, which is here, and because this capacitor is not here, it's paralleled, of course, with RL, which is our load. So if we want to find out what the input impedance is, it's RB, these two again, in parallel with R pi. But what's R pi now? Okay, well, R pi now is what it was before, beta plus 1, RE, and anything hanging on the emitter. Well, what is hanging on the emitter? We got beta plus 1 RE. Well, you've got these two, haven't you? This one here and this one here. RE and our load in parallel. So we need to parallel those two and then add them to R sub E and then multiply them by beta plus 1. So that's how we calculate what R pi is. And that comes out with an R pi of 4.4k. And so we can calculate, as we did before, the input impedance then by simply paralleling RB with this value R pi, 4.4. So it's 4.8k in parallel with 4.4k. And you know how to do that now. And that gives us an input impedance of 2.3 kilo ohms. Let's put it there. Okay, let's have a little look at the output impedance. Now, the output impedance is a bit more complex because what we're doing here is we're looking at RE. We're not even involving RL here, and you'll see why in a minute. It's because if you know anything about the emitter follower, you'll know it has a fairly large input impedance, as we've seen, 2.3k, but a very low output impedance, which enables us to drive our loudspeaker, albeit not as efficiently as a push-pull class AB, I know, but you know, it does work. So that means this value that we're going to calculate is going to be very low and almost certainly much lower than anything we're going to hang on it. So actually it will be the defining resistance rather than the load. So how do we calculate it? Well, it's RE, the resistor on the emitter, in parallel with all of this. R sub E plus RB here, this is the voltage divider parallel, in parallel with the source resistance, so that in parallel with that, divided by beta plus 1. And you just have to plug the numbers in. And when you do that, that's what you get. 620, which is our resistor here, in parallel with R sub E, 2.5, in parallel with 4.8, that's RB, the base resistor and the voltage divider, in parallel with the source input resistance, 602, divided by beta plus 1. And when you do that, you get an output impedance of 4.2 ohms. So that's absolutely fine for me to put my 12 ohms speaker on that. So fantastic, and that's what we would expect from this kind of design. And finally, just to calculate the voltage gain, and the way that you do this with a common collector, an emitter, follower, amplifier, is essentially it is RE paralleled with RL divided by R sub E plus the parallel of RE and RL, okay? And when you do that, you get a voltage gain of 0.82, and that is typical, of course, for an emitter follower, typically between 0.8 and 0.9 something. So, we talk about unity voltage gain, but it's actually a bit less. So we're actually losing a bit of voltage through this amplifier, but we're gaining a truckload of current. So that's why it's such a useful kind of buffer circuit, because it maintains and preserves most of the voltage gains of the previous circuit, but really beefs up the current that enables us to drive a lower impedance load. And so we put it in. And that, my friends, is it. Well, there you go. Now, if I'd had more time, then I would have liked to have included a section on how you calculate some of these AC characteristics using LT spice simulations, because that's quite interesting and a different way of doing it. But I haven't. And this video is way long enough. So I'm not going to go down any more rabbit holes now. I need to get back to building the direct conversion receiver. But if you are interested in that, then just go to YouTube and search for small signal analysis with LT spice, and you'll see a whole bunch of videos that come up there that hopefully will be able to help you. As for myself, I don't know about you, I'm all equationed out now, right? I need to melt some solder, which is what I'm going to go and do. I hope that you've found something useful here. If you have, please like and subscribe, and you can then be notified when I produce some more of my videos. Until the next time, thank you ever so much for watching. Look after yourself. 73. Bye-bye.